Good morning, students. My name is Shashank Shekhar, and we are doing a crash course of chemistry for the upcoming JEE exam of 45 days. And today is our 29th day. Yesterday we completed the inorganic portion, and now we will start the organic portion. So, the first chapter that we will dealing with is the general organic chemistry. So, this general organic chemistry is very basic to all the organic chemistry that we have. So, if you have to study any of the chapters of the upcoming chapters, whether it is aldehyde, whether it is alcohol, or amine, so you must be aware about this GOC. So this GOC mainly deals about the structure of the compound, the IUPAC nomenclatures and inductive effect and all, the electronic effect we have, and then it goes to the types of reaction, that is substitution, addition and all. So let us first see the JEE syllabus that is given by the NTA. So if we bifurcate it into say simpler terms or broader terms, then first we have this tetravalency and the structure. Then second we have this functional group and all. Third we have the isomerism. Then comes the nomenclature. Then comes the reactive intermediate, which are formed from the fusion of bonds, which includes radicals, carbocations, carboanions, and their stability. After that we have the electronic displacements. You know very well this displacements. You must have studied this displacement earlier also. So inductive effect, electromeric effect, resonance effect, and hyperconjugation. At last we have the various kind of organic reaction. So if you sum up all this and know all of this, you can carry out the various reactions, that is substitution, addition, elimination, and rearrangement. So organic is like a you can say a you can say like a stair. So you have to cover each and every part one by one, so that you can be excellent in the organic chemistry. Means if it is compared to inorganic, which is not that much related, but for organic it is, you can say that each and every chapter and each and every concept is correlated to each other. So you must be aware about each of them. So you can see that slowly it is building up the whole organic chemistry. Now let us move to the topic more broadly. Means I have given in a more detailed way. So first is the hybridization. Then we see that after hybridization, what are the shapes of molecule that we get. We have the functional group. Then we will see projections and all. So we will cover each of these 12 topics one by one, so that you can get a good grasp of this organic chemistry introduction. So you can consider it as an introduction part. Now let us start first with the hybridization. Okay. So if we see the hybridization thing, you must have studied this chapter earlier also in the chemical bonding. So in the chemical bonding, you have heard this hybridization term, and you must have studied also. So if you want to define the hybridization, it is nothing but a series of hypothetical steps. So it occurs in three steps. The first is the means promotion of this ground state to the excited state. Now, according to the upcoming substituent or upcoming ligands, this atomic orbital, say this, combine with each other and form the hybridized orbital. Now, what is the nature of hybridized orbital is that they all have the same energy or the equivalent energy. So you can see a schematic diagram that is put up here. So this diagram now covers whole of this concept in one diagram, or in a one picture you can say. So it is a very useful one, and I have taken it from a research paper. Now if you see here, this is the first one. A is the ground state that is given, which has so you can say two unpaired electron. Now after that, the excitation takes place, and we can see that we have four excited electrons, or you can say unpaired electron. This one, this one, this one, and this one. Okay. Now this after this excitation takes place, all of these atomic orbitals, that is px, 2px, 2py, and s, they mix with each other and forms the hybridized orbital. So I have told you earlier that the hybridized orbital are equivalent of each other, means they have the same energy. So they're equivalent in terms of energy and shape both. Okay, so this is the thing that we have here. Now according to the upcoming ligand, so it can have number of two. The number can vary from 1 to 2 to 3 to 4. So 1 can come, 2 can come, 3 can come, and 4 can come. So 4 ligands can come from any side. So according to that, the hybridization takes place. Now suppose that 4 are coming. 4 of the substituent are attached to carbon. For that case, we take the sp3 hybridization. So this is sp3 hybridization. Now if you see the energy ladder here, the 1s orbital is not involved in this hybridization. So one more point that should be kept in mind is that only the valence shell orbitals are taking part in the hybridization and not the inner shell or the inner core orbitals. Now since we require 4 or atomic orbitals, or you can say 4 hybridized orbital for the bonding, we will combine all this. So it will form a sp3, and you can see here this is the sp3 here. So this is the sp3. Now all this orbital, that is s and all the 3p orbitals, they are now at the same energy level. So this is the set of hybridized orbital. Now coming to sp2 hybridization, only two of the p orbitals combine with s orbital, and the remaining one p orbital is now at the top ladder. Now the thing to notice here is that this p orbital is up in energy, means higher in energy as compared to this hybridized orbital. Okay, so it consists of one s orbital, then px orbital and py orbital. Now coming to this sp hybridization, we have only one s and one p, that is 2s and 2px. Now this two combines and form this sp hybridized orbitals, and the remaining px and py are again at the same energy level but at a higher energy level. Now what are the points that we are getting here? The first is that all the hybridized orbital are having the same energy. Second, the number of atomic orbitals combining is equals to the number of hybrid orbital that are formed. Third one, the hybrid orbital and this is lower in energy as compared to this px and py or the px in sp2 case. So this other points which is kept in mind, and one more thing is that only the valence orbitals are taking part in the hybridization and not the inner core orbitals. Now according to this, the different orbitals have this different hybridized orbital have different shape. So sp has a linear one, sp2 has a trigonal planar, and the sp3 has a tetrahedral. Now we'll see the shapes of each of this more you can say in a detailed manner. So let us start. So this is the whole diagram of all this hybridized orbital sp3, sp2 and sp. Now for sp it is a simple one, you can see very clearly that we have all this hybridized orbital that are from this s, px, py and pz. Now this all combines and form sp3, 4 sp3 hybridized orbital. Okay, so this one is first one, second one and third one and fourth one. Now a head-on-head collision occurs to form the methane molecule, that is 4 H atoms comes and they do a head-on-head collision to form this methane here, and it is a hybridized sp3 hybridized orbital and it is tetrahedral in shape. So you can see very clearly that it is forming a tetrahedral. Now the next one is the sp2 hybridization. So what is the case for sp2 hybridization is that 1s and px and py, they both combine. Okay, now they both combine and form this sp3 sp2. So this is the first s, then p1 and p2. So sp2 is formed. Now it interacts with another sp2 and form this kind of bond. Now I have told you earlier that we are remained with one p orbital, so it can be any one. So if suppose the hydrogen atom is coming along the z axis, okay, so if it is coming along z axis, then it will be x and y. Okay, so this will be y and z, and we are remained with x1. Okay, so x1 is remaining, suppose. Now suppose this is the x orbital, px orbital, that is not hybridized. Now this two px orbital will overlap and will do a side on side collision. Okay, so you can see very clearly that there is a side overlap as compared to this one which is having a head on overlap. So one more point you can see here, that hybridized orbital are always forming a say sigma bond, and the remaining atomic orbital, that is px or py or pz, depending upon the orientation or the axis we are taking, we will have this side on side overlap and the formation of pi bond, that is pi cloud is formed. Now it is having a trigonal planar shape. You can see here that this carbon is having a trigonal planar shape like this. Similarly, this carbon is also sp2 hybridized, so it will also form this trigonal planar. So this is the case that we have here. Sorry, if you draw it more clearly, it will trigonal planar like this. So this is the triangular planar that we have here. It is triangular in shape and it is planar. So this is the sp2 hybridization. The next we have is sp. So one s and one p combines and form this 2sp, that is this one and this one. Similarly, the consecutive carbon does the same and forms the same kind of orbitals. Now these two orbitals say do head and head overlap to form this sp hybridized orbital. Now we are remained with this px and py. Now since this px and py are orthonormal to each other, sorry, normal to each other like this. So if you consider it here, this is the, suppose this is the px we have here. Now you know very well that px is aligned along x-axis and py is aligned along y-axis. So this is the x-axis and y-axis. Similarly, we have one more carbon like this. Now each of this will do a side-on overlap. Okay, this will overlap with this with this, and this with this, and they will form two pi bonds. So one atomic orbital will combine to form one pi bond. So two atomic orbitals will combine to form two pi bonds. So we have this overall two pi bonds and one sigma bond, that is due to the hybridized orbital, and sigma pi bonds are due to the atomic orbitals. And overall this shape will be linear. Okay, so sp hybridization is formed in this way. Now it is written here that this is in the plane of paper. Why? Because it is considered as the x-axis, so it is in the plane. Now this one is towards us, this one. So if I change the color here, so this one is towards us and that one is away from us. So this is a kind of, if you consider it, it is a kind of cube which is kept on the plane, and cube it is like this, or you can say cuboid more accurately. And we have all this atomic orbitals. Okay, so this is the three hybridized orbitals that we have. Now concluding this all, so if the carbon has a double bond only, so suppose it is having a double bond and two single bond, then it is sp2 hybridized. It is having, if it is having a triple bond like this, then it is sp hybridized, and it is having all single bond, then it is sp3 hybridized. So this is the concept of this shape of molecules of the hybridization. So why have we taught this? Because when you do the reactions and when the nucleophiles come, they come in the anti-bonding. Now what is this anti-bonding? So this one, the smaller one you can see here, is the anti-bonding one. Okay, so similarly we have this anti-bonding also here also, but it is not shown because it is over this head. Now the electrons or the nucleophile or the electrophile comes along the anti-bonding. So you must be aware about this thing also, because it helps in explaining many more phenomena and many more stability criteria. So this was all about the shape. Now moving up to the functional group. So we have various functional group. The first one is alkene. So you know very well. So I've just put a table that you can look, have a quick look here. So aldehyde ketone. So here it is double bond like this. Then we have this O, R. We have this OH. Then we have the amides, which is the derivative of carboxylic acid. Similarly, it is also derivative of carboxylic acid, that is acid chloride or acyl chloride. Then we have this ester, which is also a derivative of carboxylic acid. Then we have this alkyl halide. Alkyl halide will be RX. This is the amine. At last we have this epoxide. So epoxide is in this fashion. So we have this 4R group. So this R can be anything, CH3, CH2, H or anything. So there are many more functional group. Slowly and steadily when you will look at all this group and see all the reactions, you will be able to tell that which one is which one. Okay. Now let us this is the functional group, all about the functional group. So I will not talk about IPC nomenclature now. We will see this in the next class. So I've just introduced you to the functional group because many of the isomerism are based on this functional group only. Now before moving to the isomerism part, we will see what are projections. So what are projection we will see here. So the first one we have here is the Sawhorse projection. So what is Sawhorse projection? So if you look at this is the source projection of ethane, I think. Yeah, this is the source projection of ethane. So if you look at ethane, it is like this. So this is the ethane molecule. So what do we do is we take a side look here over here. Okay, so we take a side look over here and we keep all this thing. This is CH3 and this is again CH3 and this is the bond between the two carbons. So this is the carbon here and there is a carbon here. And this is called as the eclipse form. Why? Because each of this sigma bond is eclipsed, or you can say covered by the back carbon sigma bond. Okay, this is the staggered one. In the staggered case we have this alternating, so it will become more clear from this Newman projection. Okay, so if you consider the Newman projection, so in the Sawhorse projection we are taking a side view, and in a Newman projection we are taking a front view of this. So this is the carbon here, and the back circle represents the another carbon. Now, if you consider it as the eclipsed, this bond is just in front of this bond, okay, and this bond is just in front of this bond. Now, generally, this eclipsed form is less stable as compared to the staggered one. Why? Because of the bond repulsion. So this is the electron density that is present in this bond and the front one both. So if we see here, so this is having some kind of electron density, and the back one is also having some kind of electron density. Now since they are just in front of each other, there is some kind of repulsion because they both are having a negative charge. Now due to this its energy is raised, and we see that its energy is more as compared to the staggered form. Okay, and this energy is approximately equals to 3 kilocalorie per mole. So I'm just giving a data here. And if you look at the staggered form, so this is the staggered, this and this are having a angle, means it is not just beyond it, means not overlapping this bond, and this angle is called as torsional angle or dihedral angle. So in this case if you consider here, so this angle is 60 degree, sorry, yeah, 60 degree, and this whole angle is 120 degree. So this is the case of staggered. Now, if we have this common substituent that is ethane, then we have the hydrogen and we take it as eclipse and staggered. But in case of complex, or you can say different kind of substituent, we can arise at four different type of arrangements or conformations. So I will talk about this conformation later on. But to look at, if you look at here, so this is a staggered one. So this is very clear. This is a staggered one because all of this are not in front of each other. Now this is the eclipsed one. Okay, so this is the eclipsed one, and this is a fully eclipsed. Why? Because each of this hydrogen is in front of each of this hydrogen. So if you rotate this one like this, if you bring it here, you bring it there, and you bring it here, so this will form like this. F will be in front of OH, and then we will H and HH. So this is a fully eclipsed one. And then we have the skew or gauche. So what is the difference between skew, gauche and anti? Okay, so the main difference is that, so if you look at here, if you look here, you can see very clearly that this F is not here. So let me take another example to explain it. So if we take two conformations like this, suppose we are taking an example that is having a carbon, carbon, CH3, H, and C2H5. Okay. Now another example we have is CH3H and C2H5. So this is the compound that we are having. Now if we draw this, say this conformation, and we draw it like this, for the front carbon we can say it as C2H5, then H, then CH3. Now the back carbon is also having C2H5, so it will be C2H5. So I'm not taking a staggered one, do not get confused. I'm just putting this line here so it is not say covered up with this one. Suppose this is the CH3 and this is the H and this is the CH3. Okay. Now if you say that it is eclipsed but it is not fully eclipsed, so it is called as partially eclipsed. So when it will be fully eclipsed, let me draw another one. Okay. So this is the C2H5 that we have here. So if I keep the same substituent, that is CH3 and H here and the C2H5 here, then in this case we can call it as fully eclipsed. So these are the two cases of eclipsed, partially eclipsed and fully eclipsed. Now one more case that we have here is that of skew gauche and completely staggered. So if we change the substituents, suppose now if we keep this C2H5 just in front of this one, that is down, this CH3 here and this H here. Now it is will be considered as staggered. Similarly, if we can have another configuration which will look like staggered but will be called skew or gauche one. Now suppose if I put this C2H5 here, so I'm just doing a rotation, so I'm putting it here. So this will go here, H, and then CH3. Now it may look like that it is staggered, but it is not staggered because for a staggered one, this H should be just opposite of each other. So it is a skew gauche. Skew or you can say gauche both. So this was all about this Newman projection. Then the last one that we have here is called the Fisher projection or DL configuration. Fisher projection. Now for the Fisher projection, a few things are should be kept in mind that this is the most oxidized state of carbon, meaning that this carbon center that we have here, this one, is the most oxidized one, oxidized carbon, meaning it should have the least number of hydrogen or the most number of oxygen. And this carbon is the, or you can say this carbon not, let me make it more clear, so this one, and this carbon will have the most reduced one. So for getting a Fisher projection, this should be arranged in this manner. First of all, that the most oxidized carbon should be on the top and the least oxidized carbon or the most reduced one should be at the bottom. Now after that, if you look at this configuration, then how are this hydrogen and oxygen placed? So let me do it for you. Okay. So suppose we have a simple structure like this. We have this COOH here, CH2OH here, then this is H and this is OH. Now if we form the equivalent dash wedge structure, then it will look like this. So this is the dash one. or this is the wedge one and this is the dashed one. So this one is equivalent to this one. Okay, so this is about the Fisher projection. Now the conversion will look later on. Okay, so we'll not look into this right now. When we will study about this, say reaction type, that is substitution and all, then when we will have to do for anti-planar reaction and all, then we will see this conversion. Now let us move to the main topic of today, that is isomerism. So here I have put up a table here to make it more clear. So if you consider isomers, so they can be of two types. The first one is constitutional isomer and the second one is stereoisomers. The stereoisomers and the constitutional isomer. So in constitutional isomer, basically the thing is that the structure of the compound is changed, and the stereoisomer only the spatial arrangement of the compound is changed. So this is the main difference between constitutional and stereoisomers. Now they can be further classified into configurational and conformational. Now what is conformational and configurational? So if it is a conformational, then these two can be converted from 1 to 2, means it can be interconverted. They both can be interconverted just by rotation along this single bond. So if you rotate this compound bond here like this, if you bring this one down, this H will go back and this H will come front. So it will rotate like this. So if you rotate it once by 60 degree, so let me do it for you. So for this kind of question, take this projection. Okay, so this is like this, H, H, and we have this CH3, and the back carbon is having this configuration, and this compound is having like this type of configuration conformation, that is H, H, CH3, H, H, and CH3 here also. So sorry for this writing, my writing is not too good. Now if you just rotate this one, that one, this back carbon, no sorry, this front carbon, and bring it here, then you are rotating it by a 90 degree. Similarly, you will rotate this by 90 degree, this will come here, and similarly this one will come here, and we will get this structure. Now you can see that this both are interconvertible just by rotation around the along the single bond. Now the thing I want to say is that rotation along the single bond is allowed because it happens just by the isothermal temperature that we have here, that means the thermal energy that we have in the environment. So it can happen. But for the double bond, it is not possible, means you cannot rotate along the double bond. Now moving to the configurational, which is that means they cannot be interconverted by just simple bond rotation. They can be of two type. The first one is geometrical and the second one is optical. So for geometrical, we have this example, that is along double bond. Now if you want to bring this one here, simply by rotating the bond, you cannot do so because you cannot rotate along a double bond. So if you consider it like this, suppose you have a ball like this and two sticks are joined with each other. Now if you want to rotate these two balls, it is not possible at all. Okay, but if you have this single bond like this, and if you want to rotate this ball, it can easily rotate. So that is why they are not interconvertible through this rotation. So it requires breaking of bond for converting this to this or this to this. Now coming to the optical, so we will see what is optical isomerism and all. So optical are of two types, enantiomer and diastereomer. Now one thing I want to make it very clear that these two are also diastereomers. Okay, because what is diastereomer, I will make it clear later on. So diastereomer is something that is not a superimposable image of each other. So we will see it later. Now the first one, that is the constitutional isomer, they are basically of 6 types. The first one is chain isomer, so I will go through it very quickly. So in chain isomer, what we are doing is simply changing the position or changing the length of the chain. So if you see it here, So this is a 2-methyl propane, 2-methyl butane. Okay. Then when we have the 2,2-dimethyl propane. Now all this compound are just varying in chain length. Means it has a chain length of 5. This has a chain length of you can say 4. That is butane. This has a chain length of 3. And if you consider the formula, it will be same because isomer means the having the same formula but different kind of structure or spatial arrangement of the substituent atoms. The second one is the positional isomer. So in positional isomer, what we are doing basically is changing the position of the alcohol. Okay, sorry, so it will be not here. So 2-propanol will be here. So 2-propanol means we are just changing the position of AH from 1 to 2. Then we have the functional isomer. So what is functional isomer is that we are changing the functional group. So this is the ketone. Okay, so this is the ketone and this is the aldehyde. So if you look at the formula, it is same. It is C3H6O and it is also C3H6O. The only difference is that they are having different functional group. Next is metamerism. So metamerism basically means the alkyl group on the either side of a functional group are different. So it is having C2H5 on both sides and this one is having C3H7 and this is having CH3. So means on the either side of the oxygen the groups are changed. You can have a different example also for epoxide case. So suppose here is a methyl group, here is a hydrogen and here is a ethyl group. That is, so you can consider as methyl also, H and H here also. Now if you want to draw a metamer of it, we can draw it simply. Okay, then we will be remain with this C3, sorry, C2H5, C2H5, H, and it will have H on both sides. So this is also an example of metamers. Now this is not mentioned in the NCERT or in the syllabus, but we will see it in the 12th class. Okay, but it is not mentioned in this structural isomer of this NCERT book, but it is a type of structural isomer because it is change in structure and ring chain is the same case. Okay, so we will see it. So what is enol ketol isomer? So this obviously are the same thing, just we are changing the bond here from here to here, means they are having the same molecular formula but different kind of arrangement of atoms and the structure also. So it is not put up in the resonance structure because in the resonance structure we cannot change the position of the nuclei, but you see here that this hydrogen is not present here. So this tautomers are of the same functional group, means they both coexist in the solvent together, but depending upon the stability, the one will have the more population. So you know very well that keto form is more stable than this enol form. Similarly, this lactam, which is just a cyclic group of this cyclic type of this amide, which is called lactam, can also have two type of isomers, that is lactam and lactim. Then we have this amide group. Now this amide group can also form imidic acid form. So what we are doing is just putting this thing here and transferring this electron here. So we are doing a inter proton transfer. Okay, so we are just transferring proton from one place to another. Then we know that is amine group. It can also be called as imine group. Okay, so these are the basic type of tautomerism. So if you know this all four, it is enough for tautomerism part. Then next we have this ring chain isomer. So what are ring chain isomer? So ring chain isomer is that, means you see here that, okay, this is having a cyclic structure. Now you can put it in the straight chain also, just by introducing a double bond. Okay, so this is the ring chain isomer. So this is also a ring, but it is not having the same number of say ring members. It is having 5. So it is methyl cyclopentane. So this was all about this constitutional isomer. So there are basically six type of constitutional isomer. Now let us move to conformational isomer. So what is conformational isomer? I have told you earlier that they can be simple interconverted from one compound to another just by rotation. So here is a graph of the energy against conformation. जो means we are changing the position of the nucleus by rotating it along the single bond and seeing that what is the energy uh, energy energy change that we are seeing. Okay, so let us see. So this is the eclipsed one. So this is having a higher energy. Now as we move this bond here by 60 degree, we will get a different, that is a staggered one. And I have told you earlier also that due to this bond repulsion, it will have a higher energy and this will have a lower energy. So it is minima. And again if we rotate the bond, we will get a maxima and this will go on. So this process goes on in the solvent also. So whether you keep it in the room temperature, when you keep it at room temperature, this process always continues. Okay, due to the thermal energy that is present. But in major amount, this conformer is present in major amount in a given compound or given ethane. Due to this stability by 3 kilocalorie per mole, because this is lowered in energy by 3 calories per mole. This was all about the conformational isomer. So let us move to another thing, that is configurational. So if you want to know what is configurational isomer, you must know the difference. So by knowing the difference, you can easily say what is configurational. So if you see what is the difference, the conformational isomer are the 3D arrangement in space of the molecule which are interconvertible by rotation. So they are just changed from one form to another, from one conformer to another, just by simple rotation along the single bond. But configuration, so if you want to change from one configuration to another, you need to break a bond. Only by breaking and making a bond, you can convert from one configuration to another. So this is the basic difference between conformation and configuration. Now what are geometrical isomers? So if you know what is geometrical isomer, so geometrical isomer I have told you earlier that they are the isomerism that occurs due to change in the substituent on the either side of a double bond or same. Okay, so let us see what are the so we have this EZ configuration, or you can say cis trans configuration. So these are the rules to prioritize and say which one is E and which one is Z. So the first point is that we have to see at the point of difference which one is having the higher atomic number. Okay, so that if suppose we have an example, so suppose we have an example like this double bond, this is one, this is two. Okay, so if you want to name, you will name this one as one because it, sorry, this one as one because it is having a higher atomic number and this is having a lower atomic number. Similarly on this side it will be 1 and this will be 2. Now since both this 1 are on the same side, it will be called as cis, and if they are on the opposite side, they are called as trans. Or if you are saying cis, it is Z, and it is trans, it is saying E. So this is trans, this is for cis. Now if the substituents are same or identical, what we will do is that we will see the next substituent. Suppose we have this example like this. Okay, and whatever substituent, we are not considering this one. So we are saying that as we move to one bond ahead, we will see that they both are carbon. Now we will look another substituents. So two are same for both of the carbon, that is hydrogen and hydrogen. The third one is bromine, and for this one it is hydrogen. So since bromine is having a higher atomic number, we will keep it as 1 and this will be 2. Now accordingly, if it is 1 and 2, then it will be trans, and if it's the opposite case, that is 2 and 1, then it will be cis, or we can say E. Now the last condition that can arise of the multiple bonds. Now suppose we have this case that this carbon is having a multiple bond, okay, and this carbon is having all single bond. Then how we'll do it? So suppose this is chlorine and this three are also chlorine. Now what you will do is simply split this one. And how you will split? You will consider all this multiple bond as single one. Like this. Okay. So if this is broken, it will look like this. And we have this all as Cl. And this must be having, suppose it is having hydrogen. Now if you compare these two, now chlorine is same for all of this. Okay. And hydrogen and chlorine. So this one will be given as higher priority. Sorry. This one will be given as a higher priority as compared to this one. So in this way, you can say you can have three condition and you can name them as E or Z. So E of same side for same for different, and Z for same. Difference means trans and same means cis. So this is all about geometrical isomer. Now, if you consider the geometrical isomer, they are also diastereomers. Means if E and Z are both diastereomers. So just keep this in mind for now. I will later on say in detail what is diastereomer and all. Now let us move to chirality. So we know that we have covered this geometrical isomer. Now we'll move to optical isomer. So how we'll consider that something is optically active or not? So two things are to be looked upon. The first one is plane of symmetry, and the second one is center of symmetry. One more thing should be it is looked at, that is alternating axis of symmetry. But if you find out that it is not having center of symmetry and plane of symmetry, then of course it will not have this alternating axis of symmetry. So this is a, you can say, a generalization. And also you know that to find the SN it is very difficult to alternate axis of symmetry. I am not describing it here also. So that is the case for center of symmetry and for case of chirality. Okay. So let me make it very clear that chirality is not dependent or not referred to as one center or one carbon. It is considered for the whole molecule. So if something is chiral, means the molecule is chiral, not a carbon center or a hydrogen center or any other center can be chiral. It is for the whole molecule. Now what are the two elements of symmetry that should be considered? The first one is plane of symmetry. So suppose if you have a molecule, you can cut it by a single line. So it is a plane having a plane of symmetry. Okay. So you can see very clearly that this part is and this part, they both are same. So what does happen if we look at this two? So if something is having both plane of symmetry and center of symmetry, it means that their mirror image are superimposable. Okay. Okay. So this is the case. So should be not superimposable. Oh, sorry for this confusion. So this should not be superimposable on each other. So you cannot just put mirror on each and every image and find out that whether it is chiral or not. For that simplicity, we keep this two elements of symmetry and find out whether they are having center of symmetry and plane of symmetry, and then we'll say okay, this is chiral, this is not chiral. So the very basic definition of chirality is that a molecule which is not superimposable, or you can say caped on each other like this, will be called as chiral. Now if you consider this, it is having a center of symmetry. So how? So if you look at this, the compound that is given here is looking like this: CH3 and CH3. Now if you draw it in a 3D fashion, this CH3 is in the upside. If you just say, you can just put this like this on a plane, then this CH3 is the upside and this CH3 is in the downside. Now what is center of symmetry? Center of symmetry means if this is the center of symmetry for this molecule. So if you move in this direction, you will find the same substituent. Okay, so carbon is present. Now if you move downward, then you will move in the opposite fashion in the same direction. So this is the CH3. So you can see very clearly that if we move in the opposite fashion, we are getting the same substituent. So it is having a center of symmetry. Similarly, this one and similarly this one. So the center of symmetry is denoted by I, and it is also called as center of inversion. And this one is denoted by sigma, that is plane of symmetry. So if a compound is having both plane of symmetry or center of symmetry or either of them, then it will be not chiral. And for the opposite case, it will be chiral. Now what is chiral center? So I am teaching this chiral center because for RS nomenclature, we find out the chiral center, we find out the RS configuration of a chiral center only. So a chiral center is one which has all four different substituents. So suppose if carbon is having four substituents, that is A, B, C and D, then A should not be equal to B, should not be equal to C, should not be equal to D. So having four different substituents. Now, one thing I want to make it very clear here, that it is possible for a compound to have a chiral center and not be a chiral molecule. Okay, so suppose we consider a case here that this is the carbon. So I'm drawing the Fisher projection for now, so do not get hyper. Okay, so I will teach you later that how to convert from the normal molecule to a Fisher projection. Now suppose this molecule that this is the molecule that we're having. Now this is a chiral center. Why? Because all the four substituents are different: CH3, OH, H, and this whole group. Similarly, for this carbon also, we have this four different substituents. But although it is having a chiral center, it will not be chiral molecule. So this is molecule is not a chiral one. Why? The reason behind is that it has a plane of symmetry like this. So this is having a plane of symmetry. So if you look on both sides of this image, you will find a similar kind of conformation or configuration. Now due to this reason, this is not optically active. Okay, and such configuration which is having a chiral center and it is not optically active are called as metamers. Sorry, mesomers. Okay, so mesomers. So what are mesomers? So mesomers are something that meso compounds are something that which are having a chiral which do have a chiral center but they are not optically active. Now how do we find this RS configuration? Now first, the configuration should be such that the lowest group should be on the dashed one. Okay. Now next, give the priority as per the CIP rule. So the rules I have told you earlier for the EZ configuration, you will similarly name all the four substituents from the lowest to higher one. That is 1, 2, 3, 4. Now after that, if it is if it is clockwise rotation, you know what is clockwise. Clock moves like this. So if it is clockwise, then it is R configuration, and it is if it is anti-clockwise, it is S configuration. So children often get confused with this RS nomenclature. So you should practice this of question of finding the RS nomenclature so that you can make it more easier for you. Okay. Now suppose this lowest group is not on the dashed one, but it is on the wedge one. Means it is outside the plane or towards you. For that case, whatever configuration that you will get, whether R or S, will just reverse it. So suppose you are giving the lowest priority at the wedge one, and then you are seeing that whether it is R or S, and if you find that it is okay, it is S, then the actual configuration will be R1. Okay. So this is all about the RS nomenclature. Now, next thing that we have the enantiomer. Okay, so we will see what is enantiomer. So suppose these two compounds, they both are optically active. Why? Because they do not have a plane of symmetry and they do not have a center of symmetry. Okay, so this is very clear. Now if you put a mirror in front of it, you will get an image, and this image are not superimposable on each other. Okay, so now this configuration, this both of this are enantiomers. Okay, so these both are enantiomers. This is the first thing. So suppose if it is R, then it will be S, and the opposite one is possible. So you can find R and S of one, and you can tell that the other one is S. So if two are the mirror image of each other and they're not superimposable on each other, then one will have, if one is having the R configuration, then other will have the S configuration. So this is about the enantiomer. Now some properties of enantiomer if you want to consider, then enantiomer have the same physical properties but different chemical properties. Okay, so you should keep this in mind that they have the same physical property but different chemical properties. So as you will see the reactions, you will come to know that this orientation in the space is very important for the molecule to react. So if the orientation is just changed from one part to another, of course the physical properties will not change, but their chemical properties will do change. Okay, now the next thing is diastereomers. So what are diastereomers? Now this both are the mirror image of each other. Now suppose if we take two configuration that are not superimposable on each other, and also they are not the mirror image of each other. So stereoisomer which are not mirror image and not superimposable. Superimposable. If both these criteria are met, then we will call that two molecule as a set of diastereomers. Now if you see the EZ configuration like this, so this is the trans one or the E1, and this is the C1 or the Z1. Now if you put a mirror here, you will need not get this molecule because they are not superimposable on each other. Their mirror image are not superimposable on each other, and also they cannot be say converted from one to another. Okay, so they are not not mirror image which are not and not superimposable. Now due to this reason, this both E and Z are diastereomer to each other. Okay, now one thing I want to make it clear here is that in enantiomer, for a compound to for two compounds to be an enantiomer, that both of the compounds should be optically active. For diastereomer it is not important because this uh, the alkene that we are having here will do have a plane of symmetry, so it is not optically active, but it is, but this both are diastereomer. Okay, thank you. One more thing, two formulas are important. The first one is optical purity or enantiomeric axis, and the second one is alpha, that is the optical rotation. Now, if we say, tell what is enantiomeric axis, then suppose we consider example here that an SR configuration is 70% and S configuration is 30%. And if you have to tell what is the enantiomeric axis, it will be simply 70 minus 30 by 100 into 100. Okay, so it will be simply 40%. So 40% is the enantiomeric axis. So this formula I have not put up here, so I have told you this formula. It is simply R minus S by R plus S into 100. So it is R minus S by R plus S into 100. Now this is one of the formula. The second formula is the alpha observed by alpha max. Okay, so suppose a compound is showing a maximum rotation of this alpha max, and if we are observing that it is getting an observed rotation of alpha, we will multiply, divide both of this fraction, take a fraction of both of this and multiply by 100 to get our enantiomeric axis. Now how will calculate this alpha observed? So if you have a compound, then we will multiply it from the, this is a coefficient of absorbability and it is say means specific for a given compound. Then we have this concentration, then we have this L. This L should be in centimeter and this should be in the m, that is mole per liter. Now if you multiply all these three, you will get the alpha. This is the Beer-Lambert's law. Beer-Lambert's law. So this is all about the enantiomer. Now I have not discussed about this alpha and all. So what is rotation and optical rotation? So I just want to make a point here is that if you are taking an optically active compound, it will say it will rotate a light from some degree, and it can be on left side, on the right side. If it is on the right side, it is called the levorotatory, and if you're on the left side, it is called dextrorotatory. Sorry, for levorotatory it is on the left side, and for dextrorotatory it is on the right side. So the one of the property of the optically active compound is that it rotates a light of from some degree, a plane polarized light you can say, for some degree. Okay, so this is the property of light, and based upon this we can calculate the optical purity or the enantiomeric excess of a given solution. Now let us move to some questions. The first question is that we have to tell that which one is more electronegative, that which carbon is more electronegative of all this starred one. So this is the first starred one, second one, third one, and fourth one. Now we have seen what is sp3 and sp2. So this is sp3 carbon, this is sp2 carbon, this is sp carbon, and this is also sp2 carbon. Now you know very well that S is more electronegative than P. So if a compound is having a more S character as compared to P character, then it will have a more electronegativity value. So this will have a S character of 25%. This will have a S character of 33.3%. This one also. And the last one will have a value of 50% S character. So this is having a maximum S character, so it will be the most electronegative one. So this is the answer. So the same thing is written here. Now next, identify the compound that exhibits tautomerism. So I have told you what is tautomerism. So basically you have four type of tautomerism. It is ketol, enol. Then we have this amide and imine. Then we have this lactam and lactim, and one more. So this ketone cannot show this tautomerism. Butene cannot show. This phenol can show. Okay, so how this phenol can show? So if you look at the phenol, it is like this. So you can say that this is the enol form. You can also write this compound like this. Now I've told you earlier that this is generally more stable, but for the case of benzene, since we are forming a benzene ring and we know very well that it is aromatic as compared to this one, this is not aromatic, non-aromatic, because we are having a sp3 carbon here. So this one will be more stable. Okay. So let us move to the third question, that is optically active compound in all of this. So two compounds which contain the same number and same kind of atom in different spatial area but at different superimposable are called the optical isomer. You know this thing very well. Now if you draw all the structure of all of this, so what is 2-methyl pentene? So this is 1, 2, 3, 4, 5. We have a methyl here, and we also have a pentene here. So it will have one carbon, one hydrogen, one hydrogen, one hydrogen. Okay. So this carbon are not the stereo center. This is also not a stereo center, or you can say this will not have a chirality. And we know that it is a sp2 hybridized, so it will also not have a chirality. So this is not a optically active one, because all four substituents are not same. So we have one more point I want to make it here, that it should be sp2 hybridized. We will see the substituent, means if we consider the different substituent, then and then only if it is sp3 hybridized. Now for this one, it is written as 3-methyl 2-pentene. So 3-methyl and 2-pentene. this is the same case. We will not have this optical activity. Then we have this 4 methyl and 1 pentene. So 4 methyl and 1 pentene. So for this also we do not have this case. Okay, so this is the last one, 3 methyl and 1 pentene. 3 methyl and 1 pentene. So if you look at this compound, so it is having this C2H4, or so you can say 3, sorry, 3, C2H3 on this side, and then C2H5 on this side. This is the CH3 and H. So all four substituents are different. It is the CH3. So this is the chiral center, and also it does not have a plane of symmetry. Okay, so this is the optically active compound. So the answer is 3-methyl 1-pentene. Now next question, which of the following compound will show metamerism? So I've told you earlier that metamerism means on the either side we do not have the same substituent. So this is the answer directly. So it is an easy one to fall for. So we are having a C2H5 on this side and CH3 on this side. So if we consider the other one, we are having the same substituent for this also, for this also. Okay, and this is not the case of metamerism. So we have only two sides. Means we do not have the same kind of bonding. So you can see that single bonds are connected. So this will not show metamerism in any case. Okay, so it's the same thing written here, that this will not show metamerism. So this is the correct answer. How many chiral compounds are possible on monochlorination of this 2-methylbutane? So what we do, we take the four cases. So this is the compound that we have here. We do monochlorination and see all the products. So this is the first case, this is the second case, third case, and this is the fourth case. Now this is not optically active because there are two carbons, and also so this is having a hydrogen here. Okay, so the question is asked that how many chiral compounds are possible. So 1, 2, 3 and 4 chiral compound. So 4 is the correct answer. Now I will just pass on the question. I will not solve it from now. You will have to solve it by yourself. This is first question. This 5 question you will do it by yourself. Okay, so thank you for today's giving today's time. This was all about for today's lecture of the 29th day. Thank you.